Imagine this for a second. Imagine if you were wearing some kind of special glasses that turned whatever you saw into a cartoonified version of that. So if you were wearing those glasses and you looked at a chair, you would see a cartoon chair. And if you looked at a fridge, you would see a cartoon fridge. If you looked at a pencil, you'd see a cartoonified version of a pencil. If you'd worn those special glasses since birth, or if they'd been turned into contacts and just part of your eyes since birth, if you saw a cartoon pencil, you wouldn't say, oh, look, a cartoon pencil. You'd say, oh, look, a pencil. The only thing you'd ever seen in your entire life was this cartoonified world. You wouldn't compare that cartoon pencil to the real thing. To you, the cartoon pencil would be the real thing. If you saw a cartoonified fridge, you wouldn't say, oh, look, a cartoonified fridge. You'd say, that's a fridge. Because the only type of fridge you've ever seen in your life is this cartoonified fridge. That's a strange idea for us to think about because it seems so different from what we actually experience. But the simple reality is, if all you ever saw was a cartoon world, you would think that that cartoon world was the real world. But let's go ahead and do an exercise here. You see on your screen these 2 points. Here's what you're going to do. Cover up your right eye so you'll only be able to use your left eye. Then use your left eye to look at this right dot over here. While focusing on that dot, move your face closer and farther away from the screen. What you'll see is this. You'll see at some point the other dot seems to vanish. Why is that happening? Well, it has something to do with how your eye is put together. On this picture, you'll see that here in the back of the eye, that's where the where the retina is. That's where all your photoreceptors are. Light comes in here, comes over here, and it gets picked up by the photoreceptors on your retina. Here's the thing, though. At the place where the optic nerve, that's what connects your eye to your brain, where the optic nerve actually connects to the eye, there are no photoreceptors in that one tiny place. The result is that in that one tiny place, no information, no light is coming in. No light is being picked up. And so in that tiny place, your eye is actually not taking in any visual information. So why don't you see a blind spot wherever you go? Well, as it turns out, the information that's coming in from your eye is processed by your brain. Then your brain takes that process image and sort of shows it to your consciousness. The image that you see when you look at something is not the raw visual data. That would actually be very chaotic and confusing. It would be hard to make any sense of. Instead, what you see is process data. In this case, the reason that this green dot seemed to disappear is your brain was just looking at what was nearby, assuming that the same pattern would basically continue, and just filled in that says, well, if it's empty white space here, here, and here, then it's probably just empty white space here. It turned out to be wrong, but most of the time, your brain is really good at filling in that blind spot. But it has actually a very profound consequence. This experiment isn't just a cool little optical trick. It lets us know that what we see isn't actually what's there. What we're seeing is a processed image of the world. We're not seeing raw visual data. We're seeing processed visual data. We're not really seeing the world. We're basically seeing a model of the world. Or we're basically seeing a cartoon of the world. We don't think of it as being a model or a cartoon or a drawing of the world because that's all we ever see. We assume that the thing that we always see is what is actually there. But we're not actually seeing the actual raw visual data. The thing that we, quote, see is information that's been processed by your brain. A lot of times, if somebody has an inner ear infection, it will look like the room is spinning. Now, that's really weird. The inner ear determines balance, but it doesn't change what you see, or it shouldn't change what you see. It would make sense if an inner ear infection made it feel like the room was spinning, but it's strange that it makes it look like the room is spinning. Now, if you're following this idea, it's probably already figured it out, which is this. When your brain creates a visual image, this cartoon of the world for you to see, it's not just taking in data from your eyes. It's also taking data from your other senses, including your inner ear. The inner ear is seen as just as reliable or maybe even more reliable than your eye. So if your inner ear is saying one thing, the eye is saying something a little different, the brain is going to make a processed image that takes into account what the inner ear is saying. If the inner ear is saying the room is spinning, the brain will show you a visual cartoon image of the room spinning. Remember, you're not seeing raw visual data ever. You're only ever seeing this computer model cartoon data of the world. And in this case, because it's getting this information that the room is spinning from the inner ear, it's going to make it appear to actually look like the room is spinning. Ideas like this have inspired many philosophers to think all kinds of things. If we can't exactly trust what we see, it made folks like Descartes think, well, if we can't trust our senses, if we see something, for example, when we're dreaming that isn't actually there, what can we actually be certain of? And some of these are big, exciting, profound questions. You'll explore them a ton in various Bohr method worksheets. And I hope you'll also continue exploring these ideas of philosophy, reality, epistemology. That's the theory of knowledge where we ask, how do we know what we know, even outside of class and in many parts of school, if you go to college, and even outside of any of that.